let's everybody take a look in our algebra book as well. So we're looking this week starting with lesson 64, and that starts on page 260. So if you guys can follow along with me. So the book talks to us about domain, and domain sounds like an odd term. So what is domain, right? Like, have you ever heard somebody use the word domain and it's like in formal writing? Their domain, right? Well, usually domain has to do with where someone lives, right? Like their domain, where they were. Well, in algebra, we use the term domain to mean the x value. So where it's limited in the x, in the x value. So if I'm asking specifically about the domain of something, I'm asking about its x values. And you may say, well, Ms. Kim, is there another term for, since we're not talking about the x values, what about the y values? That would actually be called the range. Now, I know in math we use the word range for other things. In fact, we use the word range to talk about the difference when we have a set of numbers. The difference from the highest to the lowest is the range, right? Well, when we talk about it in algebra, so that's typically when we're talking about a group of data, we say what the range is, the difference from the highest to the lowest. When we're talking domain and range, we're talking about domain is the x values, range is the y values. So if I'm asking a specific domain or range, I'm asking on a graph, if I look at a picture of this straight line and I ask you the domain and range, both of them are all real numbers. How do I know that? Because there's positive and negative values. So my domain and range for both of these would be all real numbers. Now, your book does something where it will kind of do an italicized D, and then it'll put in parentheses reals, and then it ends parentheses. Now, it looks funny, but the reality is that all it's meaning is it can be positive and negative numbers, right? Now, if it ever confines something, like let's say that I have a graph of something that looks like this. Well, the domain is just starting here at that x. So I would say x is greater than or equal to 2 because it started here at 2 and it only goes above it. So x is your domain or your x values. Your range would be your y values. Now your book is only going into domains right now. So, but I'm mentioning to you about the range. So if you look on page 261, it's showing you on just a number graph about domain, but I want you guys to be prepared that eventually you'll have range on a coordinate grid and you'll have to do those. All right, the additive property is on page 262, and it simply means if I add the same to both sides, then I've kept the values the same. So in other words, let's say you guys had an assessment and every one of you, I added 5, except one student. One of you would say, that's not fair. Right? Because in order to be fair, we'd have to do the same to all. So I would add 5 to all assessments or, whatever takes place there. All right. Don't forget on page 262, we have open dots to signify greater than or less than. Closed dots signify greater than or equal to, less than or equal to. So those are very important. Let's take a look at our practice. And this is page 263. And it has our practice there. So it says graph on a number line. Now I was showing you domain on a coordinate plane. And don't worry, I know you're saying, oh, Ms. Kim, will we get to do that? Absolutely, my precious friends. But that's not for this lesson because they're just showing domain. And so all they're asking is on a number line. So on a number line, you would go 0, 1, 2, 3, -1, -2, opposite directions. So I've got my number line. Everybody can see that. So that's all that they're asking us to do. So it said domain is positive integers, meaning it cannot be negative. Now, it said x, on practice A, it said x is not less than or equal to -2. So remember the trichotomy principle that we had? that it can only be three things. It can be greater than, it can be equal to, or it can be less than, right? Well, if it says x is not less than or equal to, the only other thing it can be, according to the trichotomy, is x is greater than -2, right? X is greater than -2. All right, now that is where I would draw it. My domain limits where that can be. Notice next to it, it says domain is positive integers. So if x is greater than -2, it would be an open dot and going this direction. But my domain says it can't be -1. So it can only be positive integers. Well, 0 is not a positive integer, so it could be 1, 2, 3, and so on. So you would label it that way, right? So you're just putting dots at those because it's limiting it. It cannot be other things, all right? And you'll see an example. Actually, we would put a closed dot, not an open dot, because closed dot signifies that it's not that. So because the domain limited, I would put closed dots there. An example of this one would be at the bottom of page 261. They gave the same domain where it said positive integers only. And remember that integers can be positive or negative. Positive just means it can only be positive. It can't be 0. 0 is neither positive nor negative, right? I can't have a -0. I can't have a +0. 0 is just a whole lot of nothing, right, my friends? All right, so that was practice A. Now, let's take a look at letter C. Letter C says x minus 5 is not less than 0. All right, let's go back to that trichotomy principle. If x minus 5 is not less than 0, what does it have to be? Well, if it's not less than, it's greater than or equal to. X minus 5 is greater than or equal to 0. Because if it's not 1, it has to be the other two, right? So x minus 5 is greater than 0. I can solve that by adding 5 to both sides. So x is greater than or equal to 5. Now, how do I draw that on a number line? Well, let's see. I'm going to put 4, 5, 6, 7, 8 on my number line. Now, it says x is greater than or equal to 5, so that would be a closed dot. Since it's greater than that, it's going above it. So that's what my answer would look like. It can be any of those things. It can be a decimal. It can be any of those things. Oh, no, I'm sorry. I did not look at the domain. Now, that would be how I graphed it. Now, let's go back to the domain. The domain said integers only. So I have to actually put dots. But I still keep the arrow because it's any of those integers and moving forward. Guys, it's super important that you follow this and understand that my domain is being specific with me about what my answer can be. So that's why this is so important. So you have already learned how to graph this. The different part today that we're learning for this week's lesson is the domain is going to tell me specifically what my x values can be. All right, so that is super important, and that is letter C. All right, let's move on to the next lesson, lesson 65. So that was lesson 64. Lesson 65 is about the addition of radical expressions. Now, radicals are just square root symbols. We've had a lot of fun with square root symbols where that we have learned how to simplify them. But one thing I want to point out to you is that when I have a radical symbol that is the same, it's just like adding a positive or a negative variable. So if the square root is the same, then you can combine like terms. So let's look at practice A, and I'm on page 266. So I have 3 square root of 3 minus 2 square root of 2 plus 5 square root of 3. Now, when I look at that, I might be intimidated and say, wow, that's a whole lot of radicals. Well, just think of radicals as variables. 3x minus 2y plus 5x. Do you see what I did there? Square root of 3 and square root of 3 are the same terms. So I can combine 3x and 5x. I've already learned that. I'm just relating radicals to you just like you already know variables, right? So I'm not going to keep it that way. I just wanted you guys to understand that square root of 3 and square root of 3 are just like a variable. So if I have 3 square root of 3's and then I'm adding 5 square root of 3's, these are like terms. Now I have 8 square root of 3's, just like I would have had 8x. Same concept. Now, can I combine minus 2 square root of 2? No, my friends. How come? I'm glad you asked, because they're not like terms. I can hear all of you guys saying that at home. They're not like terms. They have to be the same term to be combined. So that is page 266, letter A. Now, letter B is all square root of 7, so just watch your signs, okay? I'm not going to do that one with you since they're all the same sign. But letter C is square root of 2 plus 3 square root of 2 minus 4 square root of 2 plus 6 square root of 3. Wow, I need a smidgen bigger board, don't I, my friends? All right, I'm just smearing it right in there, and I'm so sorry. I'm just trying to slide it in. So understand that this is an understood 1. 1 square root of 2 plus 3 would make 3 plus 1 is 4 square root of 2 minus 4 square root of 2. I have 4 square root of 2. I'm taking away 4 square root of 2. Friends, these all canceled out. All I have left is 6 square root of 3. I can't do anything with it. There's no other like terms. All my square roots of 2 canceled out. Final answer. Okay? So that's all that you're doing on that section of lesson 65. Okay? I do want to, before we move on to the next lesson, this is just a bonus free-for-all in there. You're doing the evens this week. So I'm just going to throw in question 20. I just saw it. It just jumped out at me. On page 267, it's a over x over 1 over a squared. Woo! I don't know about you guys, but when I see problems like that, I just get intimidated. I think, oh, that is huge. Well, remember my keep, change, flip. I can just rewrite this as a over x, keep, change it to the divide to multiply, and flip. I'm doing the reciprocal of 1 over a squared would just be a squared over 1. Wow, friends, that looks so much easier, doesn't it? Final answer, a times a squared. I'm just adding my exponents because my bases are the same. 1 plus 2 is 3 over x. A cubed over x. That's it. And that's question number 20 on lesson 65. Just a quick throw in just for fun, just because I love those. All right. Lesson 66, my friends, is on page 268. And it says simplifying radical expressions and then square roots of large numbers. We've actually done a little bit of this simplification. It's just your book is getting into some nitty gritty, right? So let's have a little bit more fun with this. So they actually gave you an example on page 269, square root of 50,000. Can you imagine square root of 50,000? Look with me on the bottom of page 269. They broke it all down for you, and then they just looked for what were the perfect squares in there. So final answer would end up being 500 square root of 2. Isn't that amazing? It's just a quick way to multiply those out. Oh my goodness, look at the bottom of page 269. Are you ready for this, my friends? 700 million square rooted. Wow. All right. Now, your calculator can give you a rounded amount, but to simplify it, not so much. Now, some calculators now, you can go into the radical mode, and it will give you that answer. But when I was your age, not so much. No comments about my age. All right, so let's jump to page 270, and let's do some of these practice with these fun, huge radicals. All right, we're about to have some radical fun, so I hope you've got your smiles on. Square root of 24 plus the square root of 48. All right, they're not like terms, but I can see inside each of those. I know 12 is a factor of each of them, so I know that I can reduce these. All right, 24, I'm just going to do 4 times 6, and then 2 times 2, 2 times 3. Quick reminder, don't forget to put your dots in between so that you're not confusing those for the number 22 or the number 23. So make sure you're watching for those. All right, so let's work on this one before we work on the next. So I'm just looking for perfect squares. So 2 times 2 is a perfect square. So since it's one match, I bring out 1, 2. How do I know that it's a perfect square? Because I know 2 times 2 is 4, square root of 4 is 2. When I find a match, I only bring out one of them, not both of them. Now, what's left? 2 times 3. 2 times 3 is 6. It is not a perfect square. It stays under the radical. I'm going to bring down my plus sign, and then I'm going to go back up, and I'm going to bring down 48. What is 48? Well, I know that is 6 times 8 is 48. 2 times 3, 2 times 4. Now, be on the lookout. I have seen students stop here and they forget that 4 is not prime. So I'm going to actually bring down 4 is 2 times 2, which is another perfect square. So I've got all of these factors for 48. Now I'm looking for perfect squares. I've got one set of 2 here. Then I've got another set of 2 here. They kind of separated there, didn't they? So I've got 2 sets of 2. So I'm going to bring out 2 sets of 2, but I'm still left with a square root of 3 that did not have a match. So he stays under the radical. So since I had 4 2's, that would be 16. Square root of 16 is 4, square root of 3. So I've got 2 square root of 6 plus 4 square root of 3. Friends, those are not like terms. So my final answer I'm sorry, I put a plus in between that and I did not mean to do that. So it'd be 2 square root of 6 plus 4 square root of 3. I cannot reduce that any further, and that is my answer to letter A. So letter A of lesson 66 is my final answer because I cannot go any further. Okay? I know that that was a lot of work, but it is just a good reminder to us of making sure if it's a radical, just like you can't combine X and Y, if they're not like radicals, you cannot combine them. All right, letter B, 2 square root of 18 minus square root of 27. Again, same thing. I'm just going to factor down each one. 18 is 9 times 2, 3 times 3 times 2. All right, I already have a number on the outside. Be careful. I've seen students miss that before. So I already have a number on the outside. So there is a perfect square inside. 3 times 3 is 9. Square root of 9 is 3. So I'm going to take that 3 out, but I've got to multiply it to what's already outside. 2 times 3 is 6. There was 1 2 that has to stay under the radical, right? Now, what is 27? 9 times 3 is 27. 3 times 3, bring down my 3. There's one perfect square, minus 3 square root of 3. Friends, are these like terms? No. It's the same thing as saying 6x minus 3y. They are not like terms because they don't have the same radical inside. If they did have the same radical, let's pretend that this was 6 square root of 2 minus 3 square root of 2. Then I could say 3 square root of 2 is my final answer. If they were like terms. Since they're not, then I know that, then I know for sure that they cannot be. All right. All right. That is letter B. Now, letter C is a humdinger, my friends. Square root of 50 million. All right. That is a lot, is it not? Now, I know that this right here would be 1,000 times 1,000. How do I know? Because 3 and 3 zeros. So I could actually just make those a match and bring those out. And then that would leave me with 50. So that would be 1,000 as a whole. Then I have the factors of 50 would be 5 times 10, 2 and 5. So I have 1, 5. So my final answer would be 5,000 square root of 2. All right. And And I thought that there was one practice like that, but I don't see it. I think it was 40,000 that we saw. So it was super close, but those are some big radical symbols. So I'm super proud of you guys. Don't let the big numbers intimidate you. You can work them all the way down. I just saw that because there were the hundreds place and there were 3 zeros, the thousands place had 3 zeros. So I just knew 3 zeros would have to be 1,000 times 1,000. That's a perfect match. So I can just pull out the perfect squares right from the start without having to multiply them all out. I do want to point out to you on page 269, they do all the work to show you how they pulled everything out. All right, last lesson for this week, lesson 67. My friends, we are on page 271. So I think that is super important to be looking at there. Page 271, lesson 67, review of equivalent equations. What they want to point out to you is as long as I multiply or divide by the same number, it's an equivalent equation. My friends, we've already learned how to substitute. So now we're learning elimination. And I'll be honest with you, everybody has favorite things. My favorite thing is elimination. I like elimination more than substitution. Now, I've had a few students tell me their favorite is substitution, but my favorite, I just love elimination. I like marking something out and saying, I've got 5 of this, I'm subtracting 5 of this, I eliminate it, now I'm down to 1 variable. So draw your attention with me to page 272, and it shows you how that elimination works. So elimination is a new method, now not new as in new to the world, but new to us as Algebra 1 students. It's also called the addition method, and in order to understand that, you have to have 1 positive and 1 negative so that one of the variables will cancel out. You remember in the substitution method, what we're doing is we're always looking for 1 variable that we can isolate and get by itself. That's the substitution method. Well, the elimination method is you're constantly looking for, let's say that everything has a coefficient and you're not able to isolate it. Then you would say, ding, 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 that's when elimination would be great. So what you do is you want 1 positive and 1 negative of the same coefficient and variable to add together to eliminate, to mark out, so that then you're left with 1 variable to solve. Then once you've solved for that 1 variable, then you can plug in that variable to solve for the other. Just like in substitution, you need to have an answer with an X and a Y. So I want to remind you in elimination, when you eliminate 1 and get 1 variable by itself, you're not finished. You still need 1 more variable to solve for. All right, so your book goes through, and I would encourage you in your own time, or when you're watching the video, you can press pause and go through some of the examples. So look at some of the examples on page 272, 273, and what they're trying to do is you're having to make equivalent equations so that you have 1 positive, 1 negative. Everybody take a look with me on page 273. Do you see how on example 67.2, I'm going to read that problem. It's 2x minus 3y equals 5. And then 3x plus 4y equals negative 18. Now, neither of those are isolatable variables. None of them have the leading coefficient 1. So what your book has shown you is in the first equation, they multiplied by negative 3. In the next equation, they multiplied by 2. Why did they do that? So both the x's would end up having the coefficient 6. 1 would be positive, 1 would be negative, and then they would cancel. So they got it down to a y variable, and then they once they solved for the y, they plugged it in and got the x. Final solution, ordered pair xy. All right, so you've learned how to substitute. Now we're learning to eliminate. Everybody move to page 274, and we're doing a very similar problem, just like the example I just showed you, and we're doing letter A. Now, when you look at letter A, you'll notice right from the start, none of them have a leading coefficient of 1. Therefore, this is not a good problem that you would be able to substitute. So instead, what we have to do is look at this problem. 3x plus 4y equals negative 7, and then 6x plus 3y equals negative 6. So how am I going to solve this? I cannot easily isolate it. So instead, what I have to do, since I cannot easily isolate it, I'm going to have to use the elimination. So the book focuses in on canceling out your x's. And either way, I don't mind. You could focus in on eliminating out your y's. So either one will work. All right. So I'm going to multiply this first equation by 2, this next equation by negative 3. So I have 1 6 and 1 negative 6. Always keep that in mind. You need 1 positive and 1 negative. So I'm going to end up, and this is the key. I've had students before just multiply the 2 by the first. Math is always fair. Algebra is always fair, even if you don't like it. But you have to be fair to all. If I multiply the first one by 2, my friends, I have to distribute that 2 to everything. All right? So that 2 gets distributed to everything. 6x plus 8y equals negative 14. Negative 6x minus 9y. Watch that sign, my friends. The negative goes to all. Equals, this is negative times a negative, makes positive 18. Now, I have distributed the same thing to each of the 1 types. The 2 went to all in its equation. The negative 3 went to all in its equation. So it's still fair. Just like in a pie, if I have half a pie and I cut everything in 2, 2/4 of a pie is equivalent to 1/2. That's all I've done. All right, is I've just multiplied it by 3. I've kept it equivalent. Now, if I add these together, the positive 6 and the negative 6 cancel, and it leaves me with negative 1y. I have 8y, I owe 9y, that leaves me with negative 1y equals positive 4. I've still got to get y by itself, so I'm going to divide by negative 1, so y equals negative 4. Now, a lot of you say, oh, I brought it down, I solved, I got 1, I'm done. No, I need an x. I've got a y, I need an x. Now, where can I plug it back in? It doesn't matter. I'll go all the way back to the top. So I would say 3x plus 4 times negative 4 equals negative 7. I just chose the top equation. So I'm substituting in my answer. So 3x minus 16 equals negative 7. Now I'm going to add 16 to both sides to solve. And I end up with 3x equals positive 9. Divide through by 3. X equals 3. Final answer, I need to write it as an ordered pair. 3, negative 4. That is how I use substitution. I'm sorry, you guys have already used substitution, so this is how I use elimination. Now, there's one more practice problem, and I want to go ahead and do that one with you just because I think substitution and elimination are so crucial for future algebra. You're going to be doing this when you get in Algebra 2. I hate to tell you this and make you scared today because it's new to you. But some problems you're going to do in Algebra 2, you're actually going to have to do this multiple times. So it's super important that you know how to set this up. All right, letter B on page 274 is 2x plus 5y equals negative 7. I'm sorry. I'm copying a practice problem and not the practice B. I'm sorry, my friends. So it's 5x plus 2y equals negative 3. And then 2x plus 3y equals negative 10. Now, in both of these practice problems, we had to make an equivalent equation for both. There are some times when you'll only have to make an equivalent equation with one of them. Now, you can choose which one you want to eliminate. I just typically go with the first if there's nothing that's easy to do. And none of them have shared coefficients or anything. So I'm going to multiply the top one by 2, the bottom one by negative 5. And that's just so that I eliminate out the x's. So let's make our equivalent equations. Don't forget the 2 has to go to all. So if the 2 goes to all, then it's going to be 10x plus 4y equals negative 6. I cannot reiterate enough how important it is to watch your signs. Watch that you distributed fairly. All right, now, the next one I'm distributing a -5. Even more crucial to watch my signs. -10x minus 15y equals +50. All right? Super important. Okay? All right, now I'm going to, just like this method is called, the addition method, mark +10 minus 10x cancels out. I'm left with -11y equals 44. Now, when I divide by -11, y equals -4. Now, I'm not done because I've got to plug that in and solve for the next. All right, so I'm plugging that in. If y equals -4, choose any equation. I usually just always go with the top one. So 2 times -4 equals -3. So I just rewrote the top equation and I solve for that. So 5x minus 8 equals -3. Again, watch your signs. I'm going to add 8. So 5x equals 5. Divide through by 5, x equals 1. Final answer is I need an x and a y. 1, -4 is my answer. So my final answer, I should always have it as an ordered pair. All right, it is a lot of work. That is my elimination method, and that is lessons 64 through 67.